Welcome back to CAP 6640. And today we will be getting started with the lightweight type of introduction to NLP, starting with some historical background and then some core tasks and we kind of types that they belong to, then kind of introduce in a leeway to the what we'll present next lecture of usable meanings and representation of languages. And so here are the here are the objectives of this lecture. We will start with tracing the historical evolution of natural language processing and the major paradigm shift that has happened there from like symbol statistical analysis all the way to deep learning based kind of approaches. Then we will look into why natural language processing understanding is hard, and then distinguish syntactic, semantic, and pragmatic NLP tasks, and the type of tasks that pertain to each of those types, and then identify core NLP tasks and their real world applications. Before we get started, a little bit of logistics. So Module 0 and Module 1 are released, and the recordings will be released soon after the lecture for those who want to use the recordings. The recommended book, somebody asked about a book, so the recommended book is released also, and it is open source book from Stanford, although it does not really cover everything that we will talk about in this lecture. Then academic activity is already posted and is going to be due on January 23rd. Grade of that activity, which is three raw points, meaning 1.3% of the overall grade, is going to count towards a bonus. So I'd encourage everyone, even if you are not really in need for that for your financial aid, to do that activity. Assignment number 1 is going to be due on January 26th. And it is already released. And then finally, the proposal was originally due on January 19th. Now, January 19th is a national holiday. And so the university mandates that you not put any assignments due on national holiday. So it's going to be January 20th instead of 19th. Okay. Any questions before we get started? Any questions? Any input? So it is an assignment there. It is bonus. And when I say bonus, in the sense that if you do it, then it counts as a bonus on top of your grade. This is like my language, like the way I use the term bonus. If you do it, it counts on top of your grade. If you do not do it, you do not get penalized. Okay? Extra credit type of assignment. Okay? So this is very important. Hear me out. Use email for all communications. My email is mohaisen@ucf.edu, david.mohaisen@ucf.edu. Any email that you can find from me straight with the university, use that email because all of those emails point to the same person, the same inbox. And the reason for that is because while I would love to track web courses, it's not the most kind of obvious kind of tool to use to me. All right. So use email. You'll get responses very quickly. If you don't use email, I'm likely going to answer you, but it's going to make me some time. Okay. So let's get started. So let's go with the historical background of natural language processing in general. So, you know, for those who have kind of been using advances in AI, particularly NLP, particularly LLMs, you think that natural language processing or the facet of natural language processing, NLP, is just a result of advances in the last 5 years. And the matter of the fact is that natural language processing as an idea started way back in the 1950s. And that was kind of the initial idea of natural language processing and linguistics in general as a computational kind of discipline. And initially, when it was discussed in the early 50s, it was thought to be a very simple task. So Basically, the understanding of the language is computationally feasible. It's very simple. You create a few rules based on some statistics, and then you can build a very fine type of system or model that can track hand-crafted rules that capture or characterize the language. And this could not be any farther from the truth. So after this initial hype, it became apparent that this is a difficult problem. Machine translation, which is basically moving or mapping a sequence from one language to another sequence, another language, was believed to be impossible because of the lack of kind of bridge or mapping between languages. And most people who have worked in that space in the 60s and 70s have abandoned the idea and kind of worked on some specific problems like grammar or whatnot for a specific language. And this is what we call the dark times or dark age of natural language processing. That is the 60s and 70s. Then comes the 80s. So there was a slow revival in that. Some efforts mainly have focused on the science of languages, what we call linguistics. And so looking into structures, grammars, and so forth for characterizing languages. Then comes the late 80s and early 90s, which is the real kind of boom of the computational natural language processing. So there was a revolution in statistical modeling of languages. And that was, in a way, motivated or kind of coupled with the increase in compute power, which was at the time significant with the rise of personal computers. And in the 90s, with even like more advances in personal computers and back-end supercomputers, things became even more interesting with the driven kind of approaches that look into ingesting a large amount of data from the same language corpora and building statistical models with some representation systems that can beat the handcrafted rules that were of the 1950s. Then things from there just kept improving. So with the advent of the internet and the kind of accumulation of a lot of data from different languages, so now you have much better statistical models that are based on real world data, and those powered by some linguistic rules. So we have now better results with even more sophisticated statistical analysis tools that look into characterizing the languages. In the 2010s, which is not very far from now, representations became an automatic drive for learning techniques that combine statistical, linguistic, and even context rule, particularly with the advance of machine deep learning type of approaches. Ben, any questions? Yes. It's a science of understanding or characterizing languages. That is a field in humanities, not in computer science or computations. So like, for example, people like to divide languages into groups of languages. That is the science of the groups of languages is in linguistics. They look into the structure of the language, syntax of the language, that is linguistics, grammar, rules that govern the language, and whether those rules are general or specific to a given language, relationship between different languages based on those rules. I guess we will talk about some of those as we talk about the tasks in a second, okay? So the distinction that we try to make here, powered by linguistics versus statistical or computational, the distinction between them is one of them is the science of the language, and one of them is the characterization of the language from a statistical, from a behavioral, from a computational standpoint. Okay, so the computer scientist versus some art people. Okay, not necessarily art, but like In fact, it turned out that the most famous person who have done some great work in computer science related linguistics or computer science language models is a somebody who's also famous in linguistics as well, Noam Chomsky, and so he's the one invented CFG, for example. Okay. Any questions? Yes.
with the big rise of like LLMs and large language models, are we like kind of in a LLM renaissance? Kind of with all the new technology being integrated on the platform.
What do you mean, like renaissance? Yeah. So the question for those who are online, are we right now with the rise of LLMs witnessing a renaissance of NLP, natural language processing? Yes, I think we are reaching a point where we have great advances that are, if we don't have any advances beyond them, then we are really in good position, in good shape. A lot of tasks can be done very nicely with the current state of the art LLMs. And yes, we are witnessing that stage. So it's accumulation of all those advances all the way from the 50s, I don't think the 50s, but like from the 70s, 80s, up to now. This is the kind of accumulation of this knowledge have produced LLMs the way that we know them. Okay, other questions? Okay, so in compute terms, we are not here for history class. So in compute terms, the early beginnings for computer scientists started with the 1950s with Alan Turing proposing the concept of machine intelligence in his work, Computing Machinery and Intelligence, introducing what we call the Turing test to evaluate a machine's ability to exhibit intelligent behavior. And so that was, what we know of the work of Alan Turing. Then in 1954, we have the Georgetown IBM experiment, which demonstrated the first machine translation system and translated 60 Russian sentences into English. By the standards of today, this is a very trivial task, but this was the early milestone that have highlighted an early machine learning advance, particularly NLP advance, natural language processing advance. So this is the 50s for us as computer scientists. And then in the 60s, 80s, we had, basically natural language processing dominated by some symbolic systems using handcrafted rules. And so these are like, when I say like, symbolic systems, these are like symbol predicate, like, if this happens to be in the given input, then do this and that. So these are like what we mean by symbolic systems. And those are built on rules that are governed by grammar. For instance, if this is the start of a sentence, then expect that to be a type of or a rule for the given word. And from that time, there is Noam Chomsky's grammar, which influenced linguistic models and enabled rule-based parsing, analysis of language structures. And we will have a dedicated part of this class on that grammar. It's called CFG, or context-free grammar. Then there is Joseph Weizenbaum, who created ELIZA in 1966. It's a computer that was one of the first chatbot programs simulating some psychotherapist capabilities. So this is a start. This is 1960s to 80s. And as you can see, fundamentals have happened in the 50s. And for this long period of time, 1960s to 80s, there were a few spotlights, but not as much of a work. Then in the 90s, like, the whole 80s, like later in the 80s, like 1987, and sometime in the 90s, we had the statistical methods that began to replace rule-based systems. And so have you ever heard of this thing called PCA, the principal component analysis, PCA? This is an old tool, but was kind of found applications for NLP or for machine learning in general in the late 80s, 1987, for instance. LSTM, the same, 1997 is the actual application of it. And as an early idea was like the 80s. So researchers have gained access to large data sets and larger compute power. And this kind of give them the motivation to study those new tools that would allow them to characterize and model languages more effectively for a range of applications. Introduction of the HMM, which is a very important kind of tool, mathematical tool for statistical analysis, and with applications in speech and text processing, was also in the late 80s. The Penn tree bank dataset, also another dataset that kind of have certain characterizations based on rules, was created by Mitchell Marcus at a time, and provided annotated Kerbera for training models. And so this was like the kind of serious start of what we see today. Then 90s and the 2000s, early 2000s, statistical NLP flourished with algorithms like n-grams, log linear models, improving tasks like machine translation and speech recognition. And I'll talk about like n-grams at length in this class. One thing I want to kind of explain is that when we say statistical NLP, there should be something as opposed to the statistical NLP. So statistical NLP is you have data, and you kind of build statistics, characteristics for appearance of characters, words, sentences, and whatnot in this corpora, in this kind of data. And it's like what we say, statistical model. So for example, if I give you a book like the Bible, and I ask you to create a language model from the Bible, then it will go over the words, occurrences of the Bible, and say like, this is the language vocab that we have. And then sentences is going to be, statistical model is going to be the frequency of how often words are combined together to construct a sentence in them, and so forth. We'll talk about that in more details. This is as opposed to some other models, other sorts of models, like a neural network model, for instance. I'll talk about those. This is just a representation, very abstract representation that makes estimation for this statistical model. Go ahead, question.
Of the natural language process that creates things like Google Translate, compared to, let's say, if you ask ChatGPT to translate something, is it a different statistical method that they go through learning the information?
As of now, there is no difference. So we'll talk about Google Translate as an early type of application that used to use statistical analysis, and it's no longer using statistical analysis. It's nowadays a neural network-based model. So right now, you would think that ChatGPT and the Google Translate for translation task is going to be the same thing, more or less. Used to be statistical model versus like, ChatGPT is a recent thing. It never used statistical analysis, used like neural network-based models from a statistical standpoint, but right now it's slightly different. Slightly different from what used to be, slightly the same. Well, it's the same actually right now. Both are neural network-based models. And again, for those who are online, for those who are going to watch this recording, the question was like, what is the difference between technology like ChatGPT and Google Translate? Right now, there is no difference between them. But historically, Google Translate used to be a state-of-the-art statistical model, not a neural network-based model. Okay. All right. So that was the early work in the early 2000s. I mean, if you remember, Google Translate was like 2005, 6, 7. And then from there, we had some evaluation kind of criteria for those kind of models. So the development of Blue Score, we'll talk about Blue Score in more details in the semester, was developed by Kishore Papinini, and it became the standard evaluation metric. It's not the best one. We right now have much better metrics for different tasks, but this was the start in 2002. And notable advancement included the Google Translate. 2006, 7 is like the first iterations of that delivers statistical translation methods. Right now, it does not use statistical method. It uses neural network-based models. Okay, and different type of ingredients of those, including transfer learning and reinforcement learning, and we'll talk about those in this semester. Okay, any questions? Good. So then we are here. So like, many of the advances that we see right now, like in ChatGPT and the likes, are a result of kind of work that happened after the year 2009. So 2009, 2010. And I have a very beautiful slide in a different talk that I gave that tracks the historical type of evolution in the deep learning type of approach to this problem. And the first of which was 2009. This is something that was called AlexNet. So somebody in University of Toronto, a student of somebody called Hinton. Anybody knows Hinton? Okay. What did he do? Come again? He invented it? Okay. Right. Yeah. That's nice. So backpropagation is an old idea. He just like made a good use for it. He's famous for like those breakthroughs. So he basically solved a long-standing problem in computer vision, which is classification. And how did he do that? He created this large data set called AlexNet. And that AlexNet is basically a mapping from objects or from like the actual image to actual objects. It was like, and then built this CNN that does the mapping automatically very well. Breakthrough, a huge one, with a bunch of ideas. Like, they are not his inventions, but with a bunch of ideas and refinement of those. So his invention is the refinement of those. So it started like 2009, 2010. And then from there, they, had some, breakthroughs with deep neural network, with something like representation, like early representation, Word2Vec. We'll talk about Word2Vec next lecture. With things like large corpora of ImageNet. Then there's like BERT, Google's BERT, and then combinations of those. So all things that we see right now are a result of that breakthrough that happened in 2009, 2010. Okay. And so from then we had like, word embeddings. So for example, Word2Vec was introduced in 2013, transformed how semantic relationships between words are modeled. So instead of just like having the word as a bunch of characters, now you have some mathematical structure. It's a vector representation that kind of capture a word and kind of carry a lot of nice features for that word. So, and then from then we had sequence modeling, although the idea started in the 1997, 1990s, late 90s. The actual good use for LSTM only kind of, came out around the time, like, 2013, 14. And that was for, again, language modeling with, the likes of GRU, LSTM, GRU, and, by LSTM and so forth for applications like translation and so forth. By the way, the invention of LSTM is subject of a great debate. So especially Schmidt-Power, this guy, or Schmidt-Upper, he's a little bit kind of angry that some people took credit for the use of LSTM, particularly those who got the Nobel Prize for it, like a couple of years ago or last year. Nobel Prize for it, got the Turing Prize for it, the Turing Award for it. So he's a little bit pissed off at that lack of attribution and credit for him, even though he has like 500,000 citations on things of similar nature. Any questions? Okay. So now this is the history, and history is great, but this class is not really about history. Here we are trying to introduce to the task that we will learn, and we want to tell you like the context of it, and then above the context we want to add a little bit of like why we study this, why it is not really something that is easy. We all speak like English, for instance, or whatever languages that we speak, Arabic, English, Korean, and so forth. So it seems to be like, well, I understand the language, I understand the rules of the language, and they are very well defined, whatnot. So why cannot we computerize this? Why cannot we just like, why not do that like in the 1950s, for example, when the concept of computer was already there? Why we could not characterize and model languages in a very easy, simple way? Come again? Oh, no, you have a large number of bits, let's say. So it should not be something to do with the language itself. It does not have to be with a computer, sorry. It has to be to do with language. Okay. Sure, this is one. This is one thing. Yeah. Languages are very highly contextual, so it's very difficult to understand the context. Yes?
So one can tell, like, when someone says a statement, what meaning what they say, like the words alone don't carry meaning.
Languages are very rich, so they can have multiple intentions, multiple intonations, multiple contexts. So that's true. Languages are by design ambiguous, yeah, and versatile.
Languages like Latin, French to English are easier, but go
They are diverse. Languages are diverse, and
you have to go through multiple steps.
you don't have to, but I get that premise of the first part of your answer, which is languages are diverse. So you can maybe like perfect a model for a language or two, but then you have like 6,000 languages in the world. Right. So some languages are very difficult to define with a closed form type of structures, like a set of rules. So they might not even have rules. So some languages are not defined with fixed set of rules. Okay.
One more, I feel like different meaning.
Ambiguity. Yeah, words can be ambiguous, can have multiple meanings. In Arabic, for example, this is one of the, I know good or bad, but like features of the Arabic language and many other old languages, is that words have versatile meanings depending on the context and depending on the context is a big thing. Yeah, context is a big thing. Okay, so now let's talk about like why NLP, natural language processing, as a computational kind of work is hard. Okay, and so I guess we will go over many of the things that you guys mentioned and here very quickly. So first of all, human languages are ambiguous. So, a word could have a meaning that depends on context that is not very well defined, just like, generally. Also, the languages would require reasoning beyond explicitly stated information. So they could be kind of implicit languages, oftentimes require world knowledge. For instance, if I say like the compounded interest. Compounded interest as two words and a phrase, it has a meaning, but in, say, for example, real world kind of domain knowledge, it's something to do with finance, right? So you have to define it, based on the context. And languages are sometimes even difficult for humans. I like to always mention this very fun fact. So in Korean language, I lived in Korea for some time to know. In Korean language, the lowest grade that students get in high school exams is for the Korean language, even though they are Korean native speakers. So some languages are difficult to get by even native speakers. Similarly for like Mandarin, Arabic, maybe now is the case, used to be slightly better, but same, I think English maybe is easy, one of the easier languages. Is it? Somebody disagrees? Well, at least like, my high school age kids, they perfect their English, right? But it's not. Oh, really? Okay.
Invent a whole other alphabet because their original alphabet was 3,000 characters long.
Right. Yeah, I mean, similarly, Korean language right now is 24, more or less, 24, because they have doubles of the characters. So 24 characters. And originally, it used to be like what they call Hanja, which is a derivative of the Chinese, one of the flavors of Chinese Mandarin, mostly. So similarly. Two systems, yeah, for writing. Yeah. So again, you have text. The text can be ambiguous, can have implicit meanings, require some world knowledge, and sometimes even difficult for humans, even native speakers, humans. So Spanish is also like similar in a way. So grammar, for those who speak Spanish, grammar is like a mess for Spanish. Gender language. Many languages have that, but like especially it's difficult. Okay, so let's have an example here. So ambiguity compounds to generate kind of large number of possible interpretations. So in English, if you can say like, I saw the man with the telescope, it has two barses. If you say like, I saw the man on the hill with the telescope, you have 5 barses because you have added this on the hill. So we kind of possibilities of I saw the man with the telescope passing on the hill is going to add 3 more cases. I saw the man on the hill in Texas with the telescope. It has 14 barses. And I saw the man on the hill in Texas with the telescope at noon, 42, and so forth. So you increase the size of the phrase, then the number of possibilities for parsing this sentence is not going to be just an increase in linear terms, but it's going to be compounding in a more exponential set of terms. And so computationally, this is going to make things very difficult. Okay. Any questions? We'll talk about those in more details when we talk about computer versus human languages. But the reason for why NLP is hard, it's ambiguous, it requires reasoning beyond explicit information, and it is difficult to even for humans. So let alone for computers. So I guess we are not here also to talk about like why it's difficult. We know it's difficult. Let's establish that, and let's talk about like why we are here. We are here to learn about some fancy, interesting kind of tasks that can be done by computers and that pertain to the understanding of a language. So we typically divide tasks in natural language processing into three broader groups. And those broader groups are syntactic ones, syntactic tasks. There are the semantic tasks, and there are the pragmatic tasks. And you can imagine that syntactic comes from syntax. Syntax means structure. And so those are tasks that do with the structure and the grammar of the language. And so you could imagine that if you are to divide a given sentence or a phrase into the corresponding parts of a speech, that is a structure. Or look into dependency, which word affect which particular word in a sentence, that is also syntax. Looking into tokenization, that is breaking a long utterance of words into parts. There's going to be also syntax structure. And the dividing or tokenization does not have to be tokenization by word, although by word is still structure. You can imagine that you are tokenizing based on actual language structure, like noun phrase, verb phrase, and whatnot in the given utterance of a sentence. Okay, so phrases, well, words are the unit of the language. The phrases are the units of a sentence, and a sentence is a unit of a paragraph, and a paragraph is a unit of utterance, like a large utterance. So you can think of tokenization as such. Okay, so this is for syntax. Syntax is to do with the structure, the grammar, and whatnot, structure. The other type of tasks is what we call semantic tasks, and semantic means meanings. And so basically, you want to focus on the meaning and interpretation of the given utterance. Utterance is just like a bunch of words coming together, and so you want to get the meaning of that. What role does this particular, bless you, what role this one particular utterance represent? It could be an entity, for example. What is an entity? It's a real world object. Could be a human, could be a place, could be whatnot, entity, right, in a language. And sometimes those entities, you need to discover them. Like I want to know if they are, when they are talking, when a given utterance is about, say, for example, Central Florida. Is it referring to the University of Central Florida, or the region of Central Florida, or the Bank of Central Florida, or whatnot? So that is what we call named entity recognition. You want to recognize an entity and kind of maybe do this resolution of this entity to know what it refers to. This is semantic meaning. You want to do sentiment analysis. For example, given a bunch of words, utterance of words, you want to tell if this is positive or negative, hateful or loving, caring, aggressive, whatnot. You can annotate that based on some sentiments, emotions. There's also text summarization. Giving a bunch of words, it's going to be a paragraph. You want to reduce that in size to convey the same meaning. This is also a semantic task. Applications could be chatbots, search engines, recommender systems. For the syntactic one, could be grammar checkers, text preprocessing. Pragmatic tasks, they combine both. So they look into context, intent, and implied meanings. Okay, so the example could be co-reference resolution. We mentioned that with the named entity recognition. In that one, you want to drive the entity with the understanding the intent of that entity is going to be more pragmatic in the sense that you want to know if this entity refers to this or that. Like a bank, is the bank of the river, or bank the bank, financial institution, bank, and so forth. Semantic is semantic is just deriving more of the meaning as a general. Here, pragmatic understanding the intent, not the explicit meaning, the intent. So you look at the task, for example, co-reference resolution here is that where you have basically two words are basically related to one another in a way, and you want to see like if this references that, if this references that in a sentence to understand the intent. Dialogue management is to understand in this particular question what context it's referring to in the previous part and so forth, to keep like the narration and the context captured. Similarly with the discourse analysis. Okay, make sense? So that one is like smaller in scope and looks into words individually and their meanings. The second one, the pragmatic task, is more of like meaning that is intent-based, that is context-based, and that is based on a large, context on different tasks like discourse and whatnot.
So when you talk about maybe analytical say that it's a semantic task. So suppose, but we can have named entities based on what the context of the sentence. Like for example, the Washington can refer to a person or refer to a place.
But it's still going to be an entity. So you want to find out those entities. I want to get like the Washington, and then like the annotation is a different story. It's an entity. I want to recognize that entity. Like I want to remove it from he and is and they and whatnot, just like the entities. Okay.
We classify it, it becomes a fragment, right? Something like that.
No, if I want to, like with the pragmatic, is like say for example, the entity Washington and it. Okay, or like Obama and he, like in the same sentence, he and Obama appear, and then you want to say like he refers to Obama but not to Joe Biden or to John McCain or whatever political figure that you can think of. Okay, that is the co-reference. In any case, those are going to be tasks that we'll explain in details. So right now I'm giving you the kind of division between those tasks and the breakdown of it. All right, so again, pragmatics, the applications are going to be the virtual assistants, conversational AI, and customer support. So we'll go in more details. So syntactic ones are to do with the structure. The example that we have is part of a speech tagging. So you identify the grammatical category of each word, like noun, verb, and adjective. This is the structure of the language. You can also look into dependency parsing, so mapping the syntactic structures to identify relationships between words, like subject-verb-object relationship between them. You can look also in sentence splitting and tokenization. That is called segmentation. If it is not at the word level, tokenization. So breaking down text into sentences and words for further analysis. The applications, again, when you say a grammar checker, like Grammarly uses kind of idea, sentence restructuring, and the pre-processing of downstream NLP tasks. The second one is okay. So we have some tasks that we can think of from syntactic. So there is word segmentation. You can break down a string into of characters into sequences of words in some written language like Chinese. So in English, it might be like a simple thing, but in some other language like Chinese, Arabic, and Korean, even Korean, you can think of that the word itself has to be broken into parts. And that kind of segmentation is not trivial, okay? Okay, so in some written languages like Chinese, words are not separated by spaces. Same like in Arabic, I know that for a fact. Even in English, characters other than white space can be used to separate words like, comma, semicolon, and so forth. So examples that we have here is, for example, a TLD, top-level domain name, or second-level domain name, like jumptheshark.com. It really is used to signify some meaning, that is jump the shark. And if you want to understand the meaning of the domain name from the domain name itself, you should be able to kind of break it down to that. And that is because this particular domain, the top-level domain or domain names, do not allow for spaces in them, okay? myspace.com, / whatever that is, you should be able to parse that accurately to kind of infer the meaning from that parsing. And similarly, so like, myspace.com, blockers weighing bar, that is the break of it, or blocker swing bar could be a different meaning. So depending on the parsing capability that you have, you'll be able to reach the meaning. Another kind of example is the morphological analysis. So morphology in the language is the field of linguistics that studies internal structures of words. So again, somebody was about linguistics. This is part of it, understanding the sounds of the languages, right? This is part of the language analysis or linguistic analysis. So that is, the field of study, and morpheme is the smallest linguistic unit that has semantic meaning. For example, you can have carry, pre, ed, li, s, whatnot. S for plural, li for adjective, ed for past tense, and so forth. Bre is before, it's a prefix, and so forth. This is for the morphemes. And so morphological analysis is, as a syntactic task, is the task of segmenting words into its morphemes. Okay, and from that you will be able to understand that a meaning, right? So with the structure, you'll be able to reach a meaning that this word itself is a verb, and ed signifies this in the past. So you understand some context. In this case, carry or carried is going to be carry plus ed, which is past tense. Independently is going to be in. Depend. In means the negation. Depend is the actual word. And int is some, like, the whole thing. Dependent is going to be a word. And then ly is going to signify something else, okay? Independently, adjective. And so Googler is the same thing, with S is being for plural, ER being for the profession, and then Google is the original word, and S for the plural, and so forth. So what is this task? Breaking things into their parts. What is it called? Morphological analysis. You want to understand, you break basically the given utterance into its basic morphemes. Okay? Any questions? All right. So this is something that here, if you went to high school here in the US, this is something that they study in ELA in high school. Okay. Some questions? Somebody raise their hands? No? Okay. So this is basic, but to kind of understand the different tasks that we have in syntax structure. Part of the speech tagging is very, very important. And part of the speech is also something that is basic in languages. But what you want to do eventually is you want to annotate a given utterance of word or sentences by their parts of a speech that they serve. They could be, verb, adjective, whatnot. Okay, and so forth. So it's useful for subsequent syntactic parsing and word scene disambiguation or sense disambiguation. And this is something we'll talk about later. Okay, so this is for syntax. Any questions about syntax? The structure. So basically, you want to understand the structure of the language based on some rules of structure. Okay. Then the next type is the semantics, basically understanding the meaning of a given language. And so it aims to capture the meaning of words, sentences, even like entire utterance of words in a text, beyond some surface level structure. Because you can imagine that the structure itself is easy, the easy part, because you have rules. You can actually encode those rules. And so the tasks that we have here include name entity recognition, NER. And basically, what you want to do is that you want to identify the proper noun, like people, like places, like organizations, etc. Word sense disambiguation. Basically, you want to tell if a given word refers to this object or that object. Determining the correct meaning of a word in context. For instance, a bank, it could be like multiple things. Bank is the family bank. Is it the river bank? Is it the financial institution bank, and so forth. Okay, it's the same like for bike. Bike has multiple meanings. Bank has multiple meanings. Color has multiple meanings, and so forth. Summarization. Basically, what we want to do is that we want to generate a concise utterance of word correspond to a larger utterance. So that is another kind of task that is semantic meaning. Sentiment analysis, you want to detect the emotions in a given utterance of words. The applications of this, we mentioned them earlier. They include chatbot, search engines, recommender systems, and social media monitoring. And so we can look into word disambiguation. Words in natural language typically are broad in meaning, so they have multiple meanings at any point in time. And so if we have this example, like Ellen has a strong interest in conversational linguistics, and Ellen pays a large amount of interest on her credit card. Interest in both utterances has different meanings. So interest means like, happy interest or desire to do something. And interest, another one, is going to be a money that you add on top of principal to pay for a bank that loans you that money. Okay, make sense? So for many tasks, question answering, translation, etc., you need to be able to understand this. You need to be able to disambiguate the word from all the different meanings. Okay, all the other different meanings. Okay, so this is for semantic. This is good. For pragmatic, it's basically understanding the context and intent of the given utterance of word. And so it deals with the interpretation of the language in context, accounting for situational factors, for tone, implied meanings, etc., etc., etc. And this is very difficult. Until recently, this was like there was a roadblock into this task. This is because languages can have like multiple meanings, people being facetious, being sarcastic, whatnot, and so this can carry more complexity on the language. So the tasks that we have here include co-reference resolution, for example, linking pronouns to or references back to the entity that they refer to. And this includes, for example, in this one, John went to the store, he bought milk. If you have somebody else before John in a sentence, like Matthew did this, John did that, and then they together did something else. They itself has to refer to the two entities, right? So you should be able to associate that. Or even you have like a noun, and then you have something in the middle, and then a reference to the first noun. That complicates the problem a little bit, and so forth, okay? So this is what we call co-reference resolution. Dialogue management, so you want to understand conversation context to maintain coherent interactions. Speech act recognition, identify the purpose of a statement. Discourse analysis, analyze how sentences connect to form coherent text. And applications is what you have at your home, like Alexa and Siri and all of that, okay? Yes?
Can it be an ambiguous co-reference resolution? Like,
yes, we'll have a whole lecture about that, and we will explain to you the case, why it is not a simple task. Like why in like everyday communications, it could be a very complex task, right? Because you can have in a single sentence, you can have multiple nouns, and then something's going to be confusing. Yeah.
Isn't it very similar to like speech art recognition, where you have to understand the intent to answer all the things?
No, you want to understand the meaning of the word individually.
But it can be incorrect, right? For example, if there is a certain word with negative entire context or nice,
that becomes pragmatic. Yeah. You mean like in sentiment analysis?
In this sentiment analysis, like given a sentence or paragraph, you kind of understand what it means in positive and negative. It's not word-to-word basis; it's more context basis, right? So just having a one negative word or one cohesive word will not qualify as negative.
And to which task you want to associate that sentiment analysis? Because sentiment analysis, the output of sentiment analysis is not really deeper. It's like still surface level meaning, in the sense that, like, we'll talk about that with actual algorithm that we will calculate as the sentiment analysis with, like, a symbol scoring function can do that. So basically, you do not really care about the individual meaning of the words. You can just like combine them, bundle them as a meaning, and then feed them in neural network and get the output, encode it in something, and then that's your score and that's your sentiment. So it's the meaning is still.
So the newer sentiment analysis models are more pragmatic, what do you think?
No, sentiment is not pragmatic. Should not be. Okay. Any questions?
So my understanding is that semantic is understanding the meaning of the singular word based on which sentence, and pragmatic is understanding the entity, the entire context of the.
Yeah. Yes. Intent beyond like surface level. Sentiment is surface level, still surface level. I know what you're talking about. It could be like, something that is more involved, more, subtle in a way that you cannot capture the actual meaning at surface level, right? Yeah, but that is a problem with sentiment analysis. Not really, does not make it a programmatic problem. Programmatic problem. Okay, makes sense? and not among those tasks. It's like, maybe language generation, NLG. It's a capability, not a task. Yeah. But you can think of it like across those. Eventually, pragmatic will combine both syntax and semantic. So you can think of it as pragmatic. Yeah.
Do like idioms and metaphors offer a particular different challenge into trying to educate these models?
Yeah.
Like as the crow flies.
It's ambiguity. Like the real world knowledge is required for that, and you can encode it.
Is it more difficult to say I went to the store?
Of course, yeah.
They're different process.
Oh, different process for what?
For understanding a common phrase like I went to the store to get milk versus another thing as the crow flies, which that sentence alone doesn't mean anything.
Right. So that is why language is context heavy. And so in order to be able to understand the meaning of as the crow flies, which is signifying distance, you have to have the context to be able to have the corresponding conditional representation of that statement that will give it the actual correct meaning. Used to be. Now it's like, comme ci, comme ça, the same level of difficulty in the sense that it is going to be representation. Okay. Because now we know how to do it, right? Sorry, comme ci, comme ça means like it's like that in French. So, but people use it a lot here.
Following question: is it possible that a particular problem can be both pragmatic and semantic? For example, we are writing a customer review feedback for one of the So sentiment analysis can be speculative, but the intent is to providing feedback or damage to the patient. So can it be an overlap?
Yes. There could be overlap. Yeah. And the example that you mentioned is a good example for that. Yeah. Other questions? Okay. So we have like 24 slides, and I'm messing with you guys. So that is scary. We have 24 slides, and we have 5 minutes. Let's go over them very quickly. Not this semester, no. So one of the pragmatic ones is coreference resolution, and we have a whole lecture about coreference resolution. So there's no point really of going over it in details. But you can imagine that, like, for example, John put the carrot on the plate and ate it. Okay, did he eat the plate or the carrot? No, for you it's laughable because you understand we cannot like really eat the plates, but the plate is the more recent one. So there is like in the resolution there is something called recency based resolution, and the computer will definitely understand that really John, what he did is basically he ate the plates. Maybe it's like edible type of plate, right? So that is the issue. So you want to basically map it to the carrot, not to the plate. Bush started the war in Iraq, depending on where you are from, Iraq, but the president needed the consent of Congress. Who's the president? It really refers in a different sentence to Bush. George W. Bush, by the way, for those who are too young to remember. Okay. All right. He's the guy invaded Iraq. Some cases would require difficult reasoning. So today was Jack's birthday. Benny and Janet went to the store. They were going to get presents. Janet decided to get a kite. Don't do that, said Penny. Jack has a kite. He will make you take it back. Which is it? The kite that he's going to give you, or the kite you're going to buy, or whatnot. So the context is really clear for us. But if you're a computer, you're not being as clear for that. Takeaway: by combining syntactic, semantic, and pragmatic. Oh, those just went off. By combining the syntactic and semantic and pragmatic understanding, NLP systems can analyze, comprehend, and respond to human languages effectively, enabling smarter, context-aware applications. And that's why I was a little bit hesitant to say, is NLG under pragmatic? And so pragmatic combines both in many ways. So it's like, if you want to just like map it to one of them, you just like put it under pragmatic, but eventually NLG is going to combine all of them. In fact, it's not a task per se that pertains to this kind of classification of tasks. Okay. Any questions? Right. So one thing I like to kind of finish with is going to be computer versus natural languages. So like why computer languages are easy, relatively speaking, you still have compilers, and it's like a whole field of study, and people do not really like that kind of class. Like, if you have compiler offered at UCF, then nobody want to take it. So it's difficult, you know, to talk about grammar, parsers, and whatnot, right? So it is very difficult, abstract. Nevertheless, computer languages are way easier than human languages. So why? Okay. So I guess it builds on the why human languages are difficult to understand. And so let's go over that. So computer languages versus natural languages. Well, ambiguity is the primary difference between the natural and computer languages, ambiguity. So computer language is very well defined, very well structured, very deterministic in a way. So you give it the right structure, it gives you the right output. It does not have any like flexibility in that space. So formal programming languages are designed to be unambiguous, very clear, just like one-to-one mapping with meanings. They can be defined by a grammar that produces a unique parse for each sentence in the language. Programming languages are also designed to be very efficient, deterministic. I don't know when I think about context or whatnot, it just, you know, give you if x equal y, do this and that. It does not, you know, basically define anything beyond that. So let's go over them one by one. Ambiguity in natural languages. So a natural language like English, Arabic, Spanish are inherently ambiguous, like examples, okay? So a single word or sentence can have multiple interpretations depending on the context and tone. The chicken is ready to eat. Are you going to eat the chicken or the chicken is going to eat, right? So this is kind of confusion. It's ambiguous in that sense. Ambiguity arises due to the factors like what we call polysemy, where words with multiple meanings like bank that we mentioned earlier. Syntax also can make it very difficult. So different grammatical structures lead to different meanings. And the pragmatics is basically understanding the intent and context influencing this interpretation. And ambiguity in programming languages, this is the opposite of it. So it's formal programming language defined formally. Every statement in the language is clear, unique in itself, achieved by well-defined grammar, like the Peckus-Nauer form, or what we call PNF, which precisely dictates the syntax and structure. And so if we say x equal x plus 1, you just like know what to do. There is no other meaning to that. Efficiency is one aspect of programming languages. So the programming languages are designed to be efficient to parse and understand and execute. So parsing basically is the process of understanding the code structure to ensure correctness of the execution. And so it's like, you know, LL, left to left, and or left to right parsers are very common type of parsers that we use. It's very efficient, so it ensures that compilers and interpreters can quickly translate the given code into some other form of code. Any questions? So what are the reasons for why, what are the comparison aspects of that? It's going to be ambiguity of the human language, unambiguity of the programming language, efficiency of the programming language. I'll wrap up with a couple of slides introducing what I will talk about next week, or actually next week, next lecture. So eventually, if you read words and have the context, you already have learned a given language, you'll be able to assign meanings to those words, okay? And so computers want to do that eventually. That is what we have, computer understanding of languages, right? And so there are many ways to do it. The initial way that I said is a statistical way. Statistical way meaning that you look at how the language is used in real life from data, and then assign codes, representations to those utterances, those words, you know, high-level words. For example, if you want to say negative, these are the words indicative of negative. If you want to say positive, these are the words indicative of positive. If you want to say, like, you know, good might mean like this and this and that, multiple words to deal with the word good, similar to the word good. So in this case, you can create, like, you know, what we call synonyms. And this will help you understand the language and use it for different purposes. If you want to paraphrase, then you want to replace the word with a word that is similar in meaning. So you can just like go to that bank of words with the synonyms, okay? And this is how it started. The whole thing started with this dictionary, or what we call word bank. Okay, and so this is a start. 2 slides, no more, and then we will dive deeper next time. What we wanted to create early on is meanings for words in computers. And so the common solution was something called WordNet, the word network, which is using the thesaurus containing the list of synonym sets and their hypernyms, or the relationship between them. And so you can imagine, this is, by the way, code in Python. You don't have to use it, but it's gonna produce. So for example, if you start with part of that WordNet, the word good, then the word good is assigned a type noun, and then good is related to goodness. It could be, the meaning of it could be commodity. Good is a commodity. It trade good, or good adjective could be good. Good as an adjective means full, means good. Good could also have something like honorable, or respectable, or beneficial, or whatnot. And so you have those meanings all together, and basically assign relationship between different words in that kind of structure. And this is what we call WordNet. Okay, this is good, isn't it? It's great, fantastic. So we should go home. There's no need to understand LLMs and NLP and whatnot, right? So what is the problem with this? Yeah, well, they can work on it, right? But I'll finish with this point. They can work on it, but it still requires some human work and maintenance and whatnot, right?
Some languages have some very structure you don't see anything else. Like Chinese are incredibly different word structure.
But how many Chinese people we have out there? It's like 1.5 billion. They can work on their language. That's not the problem, right? So that is the same problem here. I mean, right? The same problem. It's a good problem. It's not a good problem. There's no good problem. It's a problem, but we can solve it with the humans, right? Yeah. Same problem, right? It requires a lot of resources, annotators, whatnot. Seven or 6,000? Oh, they increased? I thought the languages die, not grow. 7,000? Okay. Yeah.
Have
right.
learning we speak
yeah. And Avatar, the movie, invented for us another language. So there are like 7,001, right? Yeah, Avatar is there are speakers of that language. Yeah. What is that? Oh, Star Trek. Okay, I have not watched that. So that is one thing, right? Another one is that I want to talk about our daily life. There are so many things in our daily life that just invent new words, right? So words could be more of a dynamic aspect of the language. So younger generation, I mean, I have 3 kids, college age, high school age. And then it really bothers me when they plug a word in the conversation and I really don't understand what they want. Really, speak plain English. English is not my first language, and so just be patient on me on this. So language is dynamic, right? And for the English language, you have multiple locations, south versus north. You mentioned, right? Dialects. Some nuances that are not captured. It's it keeps evolving, right? So the reason why this one is not particularly good or great, it's a great as a resource but missing nuances. So proficient is listed as synonym for good. How good is a proficient, right? Or basically in the US, we like to say oh, this is amazing. We do not really mean it. It just means it's good, right? So in certain places, or some people like me, for example, when the student asks me in my group, researcher group, how am I doing? Typically, I say it's good, which means they are doing really good, right? There is no need to use amazing or impressive or whatnot. I'll write that in recommendation letter, but I will not say that their face, right? Not to blow their ego or whatnot, right? To keep them working hard. So the language used could be very dynamic. Amazing might not mean really amazing, and good might not mean really good, or might not mean good. Or it could be the lower one of it. Good means bad, right? So there is this thing called NSF, National Science Foundation, and they have ratings like poor, fair, good, very good, and excellent. And if you have good, you will never be good. You'll never be funded. So good is not good in that sense, right? Make sense? And good in some contexts means like really great. Missing new meanings like wicked, badass, nifty, wizard, genius, ninja, bombast. Just talk to a high schooler and just learn the new language on the street right now. Come again? Oh God, yeah. They have a lot of words, new words. Yeah. There is also varying degree of subjectivity. So there is varying degree of subjectivity in the sense that your use of the word is going to be personal choice of word. Some people use words that do not really mean. Requires a human labor to create and adapt. This is the one that you mentioned, and everybody else reiterated. It's computationally, it's human intensive, and cannot compute accurate word similarity. So I said, it's a word, but like say for example, two words are going to be in different rows, and they are related to one another. Like say for example, a cat and a dog, both of them are animals, so they are related to one another. And I will not be able to tell that from this WordNet dictionary. Make sense? Unless I have a class that says animal, animal. Okay? Any questions? This is it. Any question online? Any question online? Okay, so we'll have the attendance right now. So thank you everyone who was with us online, and the recording will be made available as soon as possible. Thank you.